Once again, welcome to today's webinar focused on oil and gas industry applications. This is the third of the webinar series we're having this year. In the past, we covered two other applications, one on packer seals and another on centralizers. So these webcasts are available on our website, and you are welcome to download them if you did not get a chance to attend those. Today, we are going to look at another very interesting application in the oil and gas industry, namely pipeline inspection gauges, the instruments that are often called PIGs. With me today is Anthony Gugino, who is also currently in marketing group. Prior to joining marketing group, he worked with our services and consulting team for over 11 years. If you have attended our previous webinars, this is probably a little bit of repeated information on this slide, but however, for the benefit of those who are new to MSC Software and those joining us for the first time, I would like to take a couple of minutes to introduce our company. MSC Software is the leading global provider of virtual product development tools, including simulation software and engineering services. We've been helping companies reduce product development costs and increase product innovation for over 45 years. We provide a broad range of tools, applications, and services that help companies to virtually develop and test their products. Another core competence is the engineering process improvement that we'll touch upon briefly at the end of this webinar. Our VPD tools are all available as an integrated solution set offered through flexible licensing systems, giving you a broad range of options and the convenience of accessing MSC's entire simulation portfolio. MSC's solutions have applications in several segments of oil and gas industry. A sampling of applications includes sealing systems, including packer seals and blowout preventers, bottom hole assemblies involving contact and wear and tear studies, offshore structural analysis, safety of storage and pipeline structures, control system efficiency, turbo machinery stability and safety, and the pipeline devices used to maintain and monitor these pipelines. So with that brief introduction to MSC, let us now move on to the central topic of this webcast. After a brief review of the pipelines and the role of inspection devices, we'll go over some of the design challenges involved. After that, Anthony will introduce MSC's simulation solutions for these applications and then go over a couple of examples. We will briefly talk about MSC's solution to manage the simulation data, and then we'll have a Q&A session to address any questions that you may have on today's presentation. Pipelines are very efficient transportation systems, both in terms of operational costs and energy efficiency. The large, complex network of pipelines span over hundreds of thousands of miles across the world, and depending on the location and usage, these pipes, they're of varying diameters and going from as little as 2 inches to as big as 60 inches in diameter. So depending on the location of the wells and the final destination of the product being pumped, the pipelines may be underground or undersea or over the ground. As the oil wells are located in all kinds of climates and locations, going from Arctic permafrost region to deep offshore or very hot desert regions, these pipelines have to withstand very punishing environmental conditions, including very low and very high temperatures, humidity, wave loads, and other corrosive environments. So in addition, they should also withstand dynamic loads due to extreme weather conditions and the earthquakes as well. Failure of a pipeline, it could result in shutdown of that segment and could lead to excessive operational expenses and loss of revenue. The environmental and political impact of catastrophic failure could also be very significant. I'm sure everyone remembers the BP's pipeline shutdown 3 years ago, just when the oil prices were spiking. To avoid failures and to maintain the efficiency, continuous monitoring of these pipelines is necessary. Monitoring is also important because visual and direct maintenance is harder, since most of the pipelines, they are inaccessible, being underground or undersea. And even when they are over land, they could be in rugged terrain and making regular access very difficult. Since energy is crucial for the economic growth and also due to environmental impact concerns, government regulations affect their operations and maintenance. In the U.S. alone, National Environment Protection Act, Clean Air Act, Pipeline Safety Improvement Act, there are just a few of those that affect the installation and maintenance of the pipelines. One tool that is indispensable in pipeline monitoring and maintenance is the pipeline inspection gauge, also called a PIG. Basically, PIG is any device that is inserted into a pipeline that can travel freely through the pipeline. PIG, of course, is a backronym for the devices used to handle several operations related to pipeline maintenance and monitoring. They're used both during commissioning phase and operational phases. During construction, soil and construction debris could make way into pipelines and cause problems during operation by blocking downstream filters or damaging pump impellers and so on. By running a debris removal PIG, operators make sure that the pipes are cleaned up before usage. And often the landline debris removal operation is combined with gauging to detect any kind of dents and buckles. This ensures that there is a circular opening from one end to the other. It is even more critical in offshore operations to ensure that any areas susceptible to buckling are within the acceptable tolerances. And PIGs are also quite helpful during cleaning operation, by flooding with water and dewatering stages as well. Typical applications in operational lines include separation of products, flow improvement, corrosion inspection and inhibition, and crack detection. When multiple products are carried through the same pipeline, batching PIGs help keep the products separate, minimizing cross-contamination. And some crude oils also have a tendency to form wax as they cool, which could stick to the walls, making the surface rough and also affecting the flow efficiency. And over time, other contaminants and deposits could also gradually affect the efficiency of the pipeline. So regular pigging helps minimize these kinds of buildup. More specialized applications of the PIGs include the detection of not only dents and buckles, but also any kind of corrosion pits and cracks in the pipeline. Based on the tasks that they perform, PIGs can be classified into two main categories, utility PIGs and smart or intelligent PIGs. Utility PIGs perform a specific task in maintaining the pipeline. So examples include those involved with the debris removal, dewatering, and so on. A smart PIG, on the other hand, measures and records information that is used to assess pipeline integrity or perform non-destructive assessment of pipeline defects or bore diameter. Smart PIGs came into use in 1960s and are finding increased usage in monitoring of the pipelines. There are three main types of smart PIGs based on the technology that is used. Caliper PIGs, they have an array of levers and are connected to a recording device in the body. As the pigs travel through the pipeline, the deflections of the levers are recorded, and the results can show up the details such as girth weld penetration, pipe ovality, and dents. The next one is the MFL, or magnetic flux leakage pigs. They use a more sophisticated technique to determine the wall thickness over the entire pipe surface, as well as picking up any dents and buckles and pipe ovality, just as in caliper pigs. The principle of magnetic flux leakage detection is used to determine the volume loss of metal loss and hence the size of defect. The pigs will function in both gas and liquid lines, and since the shape of magnetic output trace has to be interpreted, the characterization is often improved by running a series of surveys over a number of years to establish the trend in the decay or damage of the pipelines. The last one is the ultrasonic pigs. They, on the other hand, they provide direct measurement of thickness. So the interpretation is more straightforward than for a magnetic flux pig. But they're better suited to liquid lines and cannot be used in gas lines without a liquid couplant. So as you see, the main advantage of these smart pigs comes down to improvement in safety and the integrity of the line resulting from the detailed survey. So when designing the smart pigs, for that matter, any of the pigs, designers should consider that these pigs need to traverse very long distances in a single run without getting stuck. And they could be run for maybe tens of miles or even hundreds of miles in a single inspection run. So retrieving a stuck pig would actually be much more expensive than a pig like just fails to perform this inspection task, but makes it to the end of the retrieval station. The pipeline diameter varies across the length of the pipe, and so the pig should also manage the transition smoothly, and the same goes with the curved sections as well. There are also several standardization specifications that need to be accounted by the designers in the designs. Obviously, physical testing of all these pigs for all the possible scenarios is not only expensive, but is also very time-consuming. So trial and error solution, it can slow things down and possibly could lead to a suboptimal design as well, because you don't get a chance to try out a lot of different variations. Simulation helps with virtual testing of the pigs prior to getting your final prototype, and thus saving your design and development and time and other costs. So at this point, I would like to turn it over to Anthony, who will discuss how simulation and specifically MSC solutions help you tackle the virtual testing issues and go over some examples. Anthony, please take over.
Thanks, Srinivas. I'll now present some topics related to multi-body dynamics modeling of pigs with Adams software. I'll start by showing where Adams fits within MSC's product portfolio, after which I'll briefly describe what multi-body dynamics simulation is and why so many companies use it. Then I'll explain why Adams is an excellent software tool for this kind of simulation. Finally, I'll present two pig modeling examples. The first comes from a project from one of our customers, and the second is an example model from MSC, which we'll investigate directly within the software. MSC's product portfolio is aligned with our customer simulation initiatives. Our customers create virtual prototypes, manage the data and processes associated with them, and partner with trusted industry experts to develop new methodology and best practices, and to apply the tools to new platforms. Supporting the creation of virtual prototypes are MSC's CAE tools. Alongside of our offerings for linear and nonlinear finite element analysis and other disciplines is the Adams product line, our core solution for multi-body dynamics. Supporting the management of CAE data and processes is our Sim Manager tool. And finally, our services team offers a broad wealth of expert knowledge and experience to assist our customers in expanding their virtual product development capabilities and pushing the envelope in the simulation world. Together, these pieces enable our customers to achieve their goals of improving and accelerating their product design cycles, optimizing the methodology of product design, and shaping the future of engineering and product development. Now we've established that Adams is MSC's solution for multi-body dynamics, or MBD for short. Well, let's answer the question, why engage in multi-body dynamic simulation at all? Why? Well, because the world is in motion. The things we work with, the things we design, the things we engineer, they all move. So multi-body dynamics is required. A few examples of things in motion related to the oil and gas industry are shown here. This is an animation of a model showing gears in a drilling application. This here is a centralizer for pipe tools. Again, an Adams model animation directly from the Adams post-processing tool. And last, far from least, the subject of today's webinar, a pipe survey device, a PIG. Okay, moving along. For those of you unfamiliar with MBD, I'll provide some background. Multi-body dynamics is the evaluation of any system comprised of bodies. In the parlance of Adams, these are known as parts and can be rigid or flexible. Acting on these parts can be a variety of constraints, either ideal or complex, as well as forces applied from external of the system or as a result of interactions between the parts. MBD solutions enable a system-level analysis, allowing us to study the interaction between multiple components in an assembly. Let me address two terms often applied to this discipline. The first is kinematics. Technically speaking, this term's application is limited to 0 degree of freedom systems. That is, a system where all of the motion is prescribed exactly. It is often used to refer to simpler analyses, sometimes even non-0 degree of freedom systems, consisting of motion-driven systems, frictionless connections, ideal joints, and the like, useful primarily for basic motion visualization. It sometimes is, but should not be confused with the second term, dynamics. Technically speaking, this term is applied to multiple degree freedom systems. In general, it's referred to as things covering to far broader capabilities and modeling complexity, such as force or torque-driven systems, realistic connections representing things like slop and friction, the inclusion of flexible bodies, contact modeling, etc. Most applications of Adams fall within the realm of what we call dynamics. Big modeling is no exception. I'll now describe some of the product design challenges to which MBD analysis is often applied. First, system-level analysis. Many design problems stem from a lack of understanding or anticipation of how a product's components interact with each other and their environment. This really requires a subsystem or even a full system level viewpoint. Let me illustrate what I mean with an example from a services project I once worked on for a customer. A brake noise warranty issue came up on a car. The OEM believed the supplier wanted blamed the supplier and wanted cost relief. The supplier couldn't replicate the noise on bench tests and believed the issue to be an interaction between the brake and the suspension. It turns out that during certain events, the brake was exciting a natural frequency in the suspension trailing arm on which it was mounted, which produced the audible noise. A detailed model of the brake on the vehicle suspension, which included a flexible body representation of the trailing arm, supported this theory. The Adams model is then used to test countermeasures on both the brake and the suspension, one of which, a stiffening ridge stamped into the suspension arm, was the solution ultimately implemented. System-level analysis is really an overarching theme that touches on many of the other design challenges listed here. The next of which is the prediction of loads. Static loads are often easily predictable and well understood. Dynamic loads, however, are far more difficult to predict and understand. Take a washing machine, for example, here, as shown in this animation. Sitting static on its suspension, it's not so complex, but place an unbalanced load in a basket rotating at several hundred RPM, and you have a more difficult problem. The movie I played showed how moving some of the components on the outside of the tub helped Sanyo reduce the displacement of one of their industrial washer designs. And determining dynamic loading is a fundamental strength of MBD and can be used to complement finite element analysis. Anyone doing component finite element analysis should ask themselves where their input loads are coming from. In cases where these are difficult to accurately predict, MBD can be used to provide more accurate input conditions, which of course result in more accurate outputs, stress histories in the case of finite element analysis. And therefore it maximizes the return on your FEA investments. With respect to pig design, determining dynamic loads due to flow or heavy parts rolling over welds and through pipe diameter transitions or bends is very important to ensure various components won't fail. Another area to which many apply MBD is geometric configuration. MBD is used in defining geometry for optimum system performance and visualizing moving parts for things like contact, interference, and lockup. Pig modeling is a natural fit here as well, since we really want to be able to assess how the various and sometimes complex mechanisms behave in all the required pipe geometries. And naturally, we'll want to assess if the pig can even make it through the pipeline at all. Vibration analysis is another area where MBD is applied. Anything really requiring frequency domain analysis is a candidate, especially NVH issues. MBD is also often used to supply an accurate mechanical model for control system modeling. After all, one needs to understand the mechanical system being controlled. This can be difficult in a system with several moving parts, complex interactions, and dynamic phenomena. MBD provides this representation. For pigs that are self-propelled by a motor as opposed to propelled by flow, this can be very useful for motor sizing and design. Naturally, MBD is an efficient solution for problems with moving parts. MSC often encounters folks trying to do too much with FEA and applying it to problems for which it's not well suited. This can cause excessive run times. An MBD solution is often more efficient than FEA for systems with many moving parts that can be represented as rigid bodies. MBD simulation enables representing flexibility and compliance only where really required. With all their moving parts, many pig applications would not be well suited at all to an FEA-only approach. Finally, like other simulation disciplines, MBD allows folks to benefit from design study, DOE, and optimization techniques by quickly assessing multiple design variants so that the interaction factors can be understood and an objective versus parameter response service can be defined. Also, it should not go without saying that, especially to those of you new to simulation in general, the general benefits of simulation that MBD practices as a subset of simulation provide as well are part of the MBD picture. Accelerate innovation by exploring multiple design concepts quickly and efficiently so you can reduce your time to market. Reduce product development costs by reducing physical testing, avoiding surprises late in the development cycle, and responding quickly to late requirement changes. The chart to the right highlights the importance in influencing the design earlier, since the cost of changes can increase as time goes on. Simulation can also help push that red curve out by providing a means to discover more impactful design changes earlier. Increasing product quality is another benefit. Simulation can help you to identify issues prior to production and reduce warranty claims, as well as quickly develop countermeasures whenever issues are discovered. Don't get me wrong, we always want to avoid and address problems upstream. The reality is that problems may still occur late and put us in firefighting mode. This is also a valuable time for simulation. Many of our customers first get involved with us during such crises and then go back later and revamp their design processes to include more simulation earlier. Well, now that I've discussed why MBD, let me touch on why Adams is an excellent choice for your MBD solution. The Adams product has over 3 decades of development, innovation, and industry leadership, and is the most widely used mechanical system software in the world. It has great depth and breadth of functionality, allowing you to address all the topics discussed earlier, and this is balanced with ease of use and customizability for specific industry applications. This is achieved through MSC or third-party product plugins, as well as by direct functionality in Adams, allowing users to customize the interface and automate the modeling process. And because Adams is the most widely used software in its space, there's a large, diverse, active user base with which to interact through conferences, our online user forums, and the like. Okay, moving on to the example section of our presentation. Let's now take a look at 2 pig modeling examples. This first one comes from one of our customers, Pipetronix. They're now a part of GE Energy. They presented this model at the 2000 International Adams Users Conference. I'll present an abbreviated version here. You can find the full presentation available for download online from the MSC website at www.mscsoftware.com. For this project, they were developing a pig to do an inline inspection of the pipeline from the Åsgard field beneath the North Sea off the coast of Norway. This pig had to be launched into a pipeline during operation and be propelled by the product flow. It would need to be retrieved up to 1,000 kilometers later. This pig was used for pipeline integrity inspection and was generated by a magnetic field to do so. A picture of the pig CAD model is shown below. The three front sections here are the tow components with seals to generate the required pressure differential to propel the pig. The middle section is the magnetizer unit, which generates the magnetic field and is comprised of 42 individual 4-bar linkages that expand and contract to keep the magnetizers close to the pipe wall. The aft sections here are data acquisition units. The primary challenging requirements for this device were as follows. It had to have a 28-inch compressed diameter at launch, must be able to travel via a service riser or be launched subsea at a depth of 300 meters. Pig has to travel the export riser base and a section of 28-inch diameter pipeline, travel the transition cone, and then travel 800 kilometers of 42-inch diameter pipeline to shore, including a landline and a crossing of 3 fjords. Now let's discuss the model a little bit. The model was started from geometry and mass properties imported to atoms from their CAD model. The flow-based propulsion was represented by 5 force elements applied to each of the 36 tow arm cup elements. These are the tow arm cup elements along here in the tow sections. The locations of these 5 force vectors are shown on the diagram here as F1 through F5. Here and here, here, and down the middle here. These forces are a function of pipe diameter, and the defining functions were based, at least in part, on empirical data. A combination of various atoms constraint types were used to properly connect the tow arm and magnetizer linkages so as to represent their ability to expand and contract. In total, 865 separate contact forces were used in the model. The force values and contact detection all referenced a Fortran subroutine, which was called by the atom solver during the simulation. This technique, while efficient, is no longer necessary, as you'll see in the next example. As you can see, this model has many repeated components in the tow arms and magnetizer. The analyst took advantage of the atom's viewability to create macros, which can be played back to quickly repeat modeling construction steps and vary the number of all of these repeated components. This model was used primarily to investigate dynamic loading of the pig's various mechanisms, especially the relatively delicate magnetizer linkages, and it was used to assess the ability of the pig to traverse the pipelines, transitions, welds, and bends. Pipetronix presented the conclusion that, quote, atoms provided comprehensive data which contributed to the understanding of system behavior prior to completion of hardware prototype and testing. These folks clearly understood the value of performing this kind of analysis upstream in the design process. So, moving along, next I'd like to show you a demonstration model of a pipeline survey device. The animation here shows the model as it traverses a sample test course, just to give you an idea of the model itself and the simulation event it traverses. Okay, I developed this model as a generic representation of a pipeline survey device. None of the geometry or model parameters intentionally represent any actual devices in production or development as far as I know, but I tried to make it somewhat representative of a likely scenario. This model is far simpler than the Pipetronix example previously shown. I have just 2 units, a front unit and a rear unit. The front consists of 8 arms which are mounted to the base by torsional spring dampers whose preloads are used to maintain contact with the interior pipe wall. The front unit is the towing unit. It has a simple single force applied down the center line of the pig that is fit with a basic PID controller to achieve and maintain a constant velocity. The rear unit is coupled to the front and pulled along. It has only 4 arms made of struts connected via translational spring dampers, which similarly are preloaded to maintain contact with the interior pipe wall. The simulation event is defined here on this slide as follows. The pig reaches a 0.5 meter per second velocity in a 0.7 diameter section of pipe here. Then it traverses this straight pipe up to a transition cone that moves it from 0.7 meters up to 0.85 meters. The transition cone spans 0.75 meters. And then it traverses a 90-degree bend with a curve radius of 3.6 meters until it reaches another straight section of pipe and finishes. The key feature of this model from a product functionality standpoint is that it takes advantage of the most recent generation of Adams contact modeling capabilities. Back in 2000, none of this functionality was built into the tool directly, so they had to write their own functions and chose to do so via an integrated Fortran subroutine, as we learned just moments ago. Since then, several types of contact modeling capabilities have been built into Adams. Today, these include solid-to-contact for 3D rigid and solid-to-solid contact, for 3D rigid and 3D flexible bodies, as well as contact for rigid body 2D elements. Any combination of supported bodies is allowed. Also, spheres are treated with an analytical method which uses the geometric property of the solid to reduce the time required to compute contact information. Other rigid solids use the so-called rapid method, which uses tessellated surfaces to detect contact. In the MD Adams 4 release coming up this December, the analytical method will be expanded to cover ellipsoid, cylinder, and box geometry. I built this pig model in a pre-release version of the Adams R4 code and took advantage of the analytical contact in the cylinders for my 12 wheel-to-pipe contacts, all shown here with the force vectors highlighted showing the contacts. So I'll now switch to an Adams session so we can take a closer look at the model live in the software. So this is Adams, and this is the model. In the software preprocessor Adams View. Let's take a look at the contact forces. Let's take a look at one of the contact forces here between one of the front arms and the pipe. If I select Modify, you can see all the properties of the contact force. Very simple. It simply bases itself on two solids, any two selectable geometries. So it's very quick to create. I have some settings here that define how the normal force is defined. We use what is called an impact function in Adams, basically a Hertzian stress theory-based contact model. So it looks for a intersection of two solids and then applies a stiffness, which is raised to a certain exponent, as well as applies a damping that's ramped on to a certain across a certain penetration depth. Friction is also modeled in these contacts, a Coulombic friction model with a static friction coefficient and a dynamic friction coefficient, which transition across a given velocity span. Just to look at the ease of creating these contacts, we'll actually delete this contact here and recreate it briefly. So in order to do this from our force palette, simply select the contact force item, and then I can simply pick the contact solids I'd like to use, either directly clicking in here or right-clicking and finding the cylinder I'm primarily interested in. So I picked the two solids, and that's all that is determined, that's all that is required to determine the bodies that are going to contact. I don't need to set up any predefined contact regions or contact detection regions. Just simply tell it two bodies, and whenever they contact, please turn on the force. Defaults are applied here. I've fully parameterized the model so we can actually look at referencing design variables for these things. So I've set up design variables for all of my contacts. So I could apply my own contact design variables here, wheel contact K, the same one that's used in all 12 of my contacts. So all I need to do if I would like to change the contact parameters is edit any of these design variables. And we'll go through and fill all these in, but you get the idea. Very easy to create this contact, and all of a sudden there it is. My contact force element has been created and it exists. There are also springs in this model. As I mentioned before, you can see the preloaded springs are existing at the bases of both of the front and rear units. Their properties are parameterized as well. If we look at one of these springs, we can see again we're referencing design parameters for these three spring properties. And again, because these are spring properties that cover all the various front springs, for example, I can modify those single properties by something like our table editor here. I can go through and modify any of the spring preloads in the front or the rear, or any of the other spring properties in the front and the rear, very quickly and very easily through this interface. So let's take a look at the post-processing tool. This is the tool I used to create some of the animations you saw, and it's also the tool we use to investigate any of the results, both plotted and animation, as you can see here. So what I'll do here is animate the model and run it through its course again. This time we've got a four-view look at the model, three animations rolling here, all staying in sync, as well as staying in sync with this plot. So you can see as it just runs through the transition there, you can see the contact forces and the wheels drop a bit because obviously the spring preloads they're unloading themselves, so they're not pressed up against the wall of the interior of the pipe so much. And as we skid around the curve, some of these forces actually occur a little more forces are getting driven into the curve by spinning around the curve. And the red line here shows the velocity, shows that we're holding it roughly at 500 millimeters per second. Again, not perfect because it's held by a controller, so very true to life. Okay, we'll now return back to the PowerPoint presentation. So I'll conclude. Let me reiterate the motivating business factors driving MBD analysis of pipeline survey devices like PIGs. There are two main factors here. One is to reduce the amount of costly physical prototypes required to get to a final product, and another is to avoid costly problems in the field, such as component failure, for example, a linkage breaking off, or pure PIG immobilization in the pipeline. Some PIG-specific design challenges which Adams can address to achieve these motivating goals are listed here. First is basic performance visualization to determine if the PIG can make it through the pipe. Secondly, Adams models are excellent tools to determine component loading history from the complete dynamic system over the whole extent of an event. Another application is for mechanism sizing, be it spring properties, linkage dimensions, or understanding how these may be influenced by the effects of flexibility in the parts and connections. Motor development is another application well suited to Adams. One could use such a model to define the force and torque requirements of a motor, the driving motor, or more advanced, integrate the mechanical and control system models together. Adams offers a complete set of options here. And last but not least, we are constantly pleased and surprised with the diverse and creative ways with which our customers successfully use Adams. I've no doubt that the oil and gas industry will continue to innovate in this regard. So with that, I will turn it back over to Srinivas.
Yeah, thank you very much, Anthony. I hope you saw the tremendous value that Adams brings to simulation of these very complex mechanical systems. I would like to switch gears now and talk about another but often ignored aspect of simulation, namely the simulation management itself. Using simulation often creates a lot of valuable data, which means any type of data that is relevant to simulation, all your models and model configurations, your CAD/CAM files, and your results or material properties, or any other type of method or template file that generated content for you. So if these massive amounts and various types of simulation data are not managed effectively, it could result in poor reuse and knowledge sharing, in addition to communication and process inefficiencies within the company. So the real challenge is to get the simulation work done, but better, faster, and cheaper, and be able to run more and more simulations and improve the credibility of simulation by having a complete audit trail information linking these results back to a design alternative that has been analyzed. SIM Manager from MSC Software offers the possibility for everyone to collaborate and get their simulation work done better, faster, and more reliably. It is a web-centric framework for sharing, collaborating, and controlling simulation data and processes. It represents the software infrastructure that will securely store, protect, and tie together all of your simulation activity. It is built using a services-oriented architecture, making it easily extensible and customizable to meet your needs. So through this web-based platform, your simulation data will be securely available around the globe, version controlled, and with secure role-based access control. So one last point before we get to the end. In addition to providing simulation software, data, and process management solutions, MSC also has a large services team placed across the world to assist our customers to quickly realize and enhance the value of their investments by executing simulations and training your employees and automating processes or implementing web-based systems to manage and coordinate the simulation of the data. They can engage with you on many different levels. So with that, let me summarize what we have covered in this webcast. Using MSC's simulation solutions, we have demonstrated how to analyze a complex system such as the pipeline inspection devices. So in doing so, we demonstrated how multi-body dynamic simulation software like ADAMS can be used to virtually test your mechanisms and contact interactions between all the components of your entire system. So we have also explained how MSC can provide simulation data and process management that can help improve your productivity. So in summary, MSC's solutions come with the advantages of providing accurate and robust solutions within a complete simulation framework, including your process management. So once again, thank you very much for taking time to attend this webcast. Please stay online for a question and answer session to follow.